Okay, welcome everyone. So it's very nice to have you here, the ones that are here in person, and also for the people in Zoom. So today is a real pleasure to have with us David Keys. So he directs the Extreme Computing Research Center at KAUST, and he got his PhD from Princeton in aerospace and mechanical engineering, and then applied math from Harvard, if that's correct.
Undergrad mechanical.
Undergrad mechanical. Yeah. So then he has many actually awards, and he has a really outstanding record. So I just was reading about what you have done, and it's really very impressive. You have participated in the ASCII program. You have also a Gordon Bell award, and you also served you were the founding dean actually of the KAUST in 2009. You have contributed and collaborated with the Department of Energy, the NASA, many awards like a fellow of the SIAM. So I think that today we are going to talk about nonlinear PDEs and preconditioners, so just go ahead with it.
Thank you, Adrian, and thank you all. It's such an honor and really a pleasure to be at MIT anytime, but especially as we emerge and have at least hybrid meetings. I think it was 3 years to this month that I was last here in a CCSE symposium, and so it's appropriate, I mean, to me anyway, it's very exciting to be sort of re-entering physical seminars right in this context. And thank you, Adrian, for that introduction. I would like to speak about something that's fairly simple, but I think very practical, nonlinear preconditioning. And where we're going, just so you know whether you want to stay tuned in, is we're interested in systems that are nonlinearly stiff, such as, for example, a reservoir modeling problem. This is the famous SPE-10 model, Society of Petroleum Engineers. It's like the NACA 0012 or the driven cavity as the standard thing you have to do in other fields. And this is a water injection into an oil reservoir with a recovery in the corners. And if you solve implicitly with Newton's method on each time step in a progressive discretization of the overall system, you see the convergence is relatively slow. That's the 6th, 8th, and 10th time steps in black there. Whereas there's very simple preconditioners that I'll get to, partway through the talk, can converge in many fewer steps, and as a net savings in CPU time. There is an extra cost per iteration, but the savings in all those non-productive iterations will pay. So why are we going there? Newton's method is independent of the spatial resolution, typically, of nonlinear PDEs that it is called upon to solve, but the embedded linear solves are not. Typically, a condition number like the inverse square of the mesh spacing. So you can often spend 90% of your time in applications like reservoirs, combustion, aerodynamics, and so forth, just solving linear systems if you go fully implicit. And they're also the most memory demanding and least scalable part of the code. So the best way to get rid of them is to do fewer Newton solves requiring them. Of course, also work hard on linear preconditioners, and that's a separate talk. And the motivation for this talk could be derived, say, from Hamdi Chelepi's paper from CMAIM in 2019, saying, the strategies to address the intrinsic nonlinearities are still an active area of research. So what is nonlinear stiffness? It's not a precisely defined term. Neither is linear stiffness. But if you take the formal definition that you can find on top, practically a linear system is stiff if the stability requirements are more strenuous than the accuracy requirements. You could, from an accuracy point of view, take a much larger time step, but stability restricts you. So analogously, a nonlinear system we call stiff if some components of the overall Newton correction, typically a small number, force a small Newton step for convergence within some robustified Newton solver, while most components could take the full step. And the origin of nonlinear stiffness, of course, is that in a Newton algorithm, we truncate the multivariate Taylor expansion to just the boxed terms. F prime is the Jacobian. We invert the Jacobian on the negative of the residual to get a step. And then that Jacobian linear solution is usually done inexactly with some preconditioned Krylov solver or preconditioned, some maybe with domain decomposition or multigrid as a linear solver. The problem is that when those high order terms dominate, the linear model is not a good approximation. And here's an example of varying Reynolds number within a driven cavity. So the Reynolds number is the only multiplier of the nonlinear term. If it's 1 or 100, Newton converges from an initial steady state very quickly. If it's above about 770 in this particular discretization, Newton will stagnate forever. And the question is, can we do better? And the answer is that indeed, there are many sort of cheap, simple to code ways that reuse modules that are probably already in the PDE code. In reservoir problems in particular, there are many sources of nonlinear stiffness, the heterogeneous permeability or porosity, the relative permeability functions, the spatially varying capillary pressure, faults, channels, voids. Any one of these could, without much hint as to where the problem is, cause Newton to damp to death or to proceed extremely slowly. And this erodes why we want to go fully implicit in the first place, which is to advance on truncation error in time alone, and even to go higher order in time. So enter nonlinear preconditioning. It's going to perform nonlinear relaxation within one or more subsets of the original equations and unknowns. And it's going to be accelerated by a global Newton method. So this is very analogous to the terminology of linear preconditioners with an accelerator, which in that case is Krylov. And indeed, the whole machinery of Newton preconditioned Krylov is going to be re-employed in this context in the outer level as normal, and then within the individual subcomponent solves as well. And the prime consideration in selecting the inner nonlinear preconditioning is ultimately how well can the outer method still be preconditioned on its own terms. The original nonlinear preconditioners, ASPIN and MISPIN, which go back to 20 years ago, in 2002 actually, in CISC, they complicated the outer preconditioning by replacing a sparse outer Jacobian, the native finite discretization Jacobian, with a dense one where there were all these blocks from the sub-problem eliminations. Right preconditioners retain the original Jacobian, and the news really in this talk is that there's a new left preconditioner which enables you to reuse the original sparse Jacobian. And it's actually quite similar to INB-NE, the nonlinear normalization one, but it's not identical, and it's interesting perhaps to compare the two. This talk is drawn from a series of papers with the collaborators at the top. Lulu Liu, a former PhD student of mine at KAUST, Li Luo, especially a former postdoc at KAUST, and my very first postdoc about 25, 30, 35 years ago, I don't know, Xiao-Chuan Cai, who is currently at Boulder and the University of Macau, and who I consider really the dean of nonlinear preconditioning. So the scope for this talk is to introduce a two-component problem just to see how nonlinear preconditioning works, then to introduce it with a 1D and a 2D set of problems that enable you to see how to identify, in some cases, where the troublesome degrees of freedom are graphically, and then to look at performance on a responsibly discretized, serious problem. And then I will, after I get to that point, go back a little bit into the history of the original nonlinear preconditioners and talk about some additional features like adaptive switching back to full Newton off of the nonlinear preconditioned and getting error bounds on output functionals, which is another way of terminating early depending on the quantities of interest. I won't spend any time of this talk doing derivations, but there are plenty of references. I'll blaze through a couple maybe. So the classic algorithm before nonlinear preconditioning is inexact Newton with backtracking. Inexact refers to only approximately solving the Jacobian correction equation. Again, this is the residual, the original Jacobian, and we would ordinarily, in the strict Newton method, set that term to 0. Instead, we bound it by a succession of norms of the original nonlinear root finding problem and a set of factors eta that converge to 0, ending up with a strict Newton method, but not working too hard in the initial stages. And this actually, the backtracking goes back to Armijo in 1966, a 3-page paper, one of those classic papers that really defines the future of a field in terms of adjusting the magnitude of the Newton step in order to find a globalization. So left preconditioning solves an equivalent system. F of x equals 0 is our system, and we transform the equations to get a script f. There are many things in the literature, and right preconditioning, in effect, displaces the initial unknown vector based on solving some subsystems, and comes up with the original problem on a new start. So this is analogous to linear preconditioning. We have linear on the left, nonlinear on the right, left on the top, right on the bottom. This is what you're familiar with. You scale the unknowns in right, you scale the equations on the left in linear preconditioning. You try to find an M inverse, which is the approximate inverse of A. And in nonlinear preconditioning, as I've already intimated, we either rescale or reform, really, the equations. It's not just a matrix scaling or reposition the starting vector. With apologies to Tolstoy, all linear problems are alike, but each nonlinear problem is nonlinear in its own way. And in the spirit of that, I throw open this lecture to collaboration afterwards. If you're stuck with a nasty Newton problem, you probably are going to invent a new nonlinear preconditioner, or at least a new heuristic for identifying the unknowns that should be treated in a special way. And that's actually where the main contributions remain. But let's start with a 2-equation problem in 2 unknowns, x1, x2 in the coordinate plane. Here is the root of that pair of equations. It's the point 1, 1. And if we start from these various corners of this rather steep plot of the, if you will, the merit function with the root right at the bottom, you see that a standard Newton method starting from the upper right corner takes, I think it's about 13 steps there, and it even overshoots the root at the beginning, whereas the algorithm that I'll very briefly and very quickly introduce finds the root in a much smaller number of steps. And it does that by replacing the top equation there, which identifies as the bad actor here, with a simpler equation. So you'll note that the point 1, 1 is the root of both of those sets of equations. And how did we get the second one from the first one? Show you just in a slide or so. But here is the result. If we try to find the root from these 4 corners, the nonlinear elimination precondition inexact Newton will always beat the standard inexact Newton with backtracking by some measure. It uses inexact Newton with backtracking as the outer method, but it just does some extra work. So let's look at a more formal presentation where we break a system of nonlinear equations into the bad unknowns and the good unknowns, and associate the equations diagonally. Usually that's easy to do with a PDE. You know which conservation law is centered on which degree of freedom. And so this is a 2-way partition. We could have multi-way partitions. But we are going to eliminate the bad degrees of freedom, that is to say, solve the bad equations while keeping the good unknowns fixed. So this is sort of the preconditioning step. We're going to displace the bad unknowns by a Newton correction, TB, which is found by solving an equation labeled 8. Then we're going to form a new set of nonlinear equations to solve by a standard Newton method. And they consist of replacing the bad FB with this scaled version of the correction. And the scaling is just the section of the original Jacobian that corresponds to the bad unknowns. And then you feed that into a standard Newton method, except that the right-hand side is changed, and take a corrected update. Very often that lambda can be 1 after we've done preconditioning. So where did that come from? Well, it came from formally defining a new script f, where the bad fb is replaced by tb, and then solving if you look at the Jacobian script j of that script f and just work it out with the chain rule, you see that it basically is the Jacobian of the original problem with a shifted argument, where u is this correction, and this diagonal scaling. And since this is a particularly simple form, we can just multiply through by this upper block and clear this inverse, and we end up with the original Jacobian and just a scaled right-hand side. So very simple. And the code, the pieces you need are already in your code. A right preconditioned version of that same concept, which starts with eliminating the same degrees of freedom in equation 17 and solving a similar linear system for the Newton correction. It differs by the right-hand side not being so scaled and the starting vector being displaced. So it basically has the same 4 steps, but it's not an identical method, and you can compare them slightly later in this presentation. So let's go to a one-dimensional boundary value problem. This is transonic flow in a converging, diverging nozzle. We have density, rho, and a velocity potential for the averaged x direction velocity, phi. And here's the parabolic cross-sectional area. And those familiar with fluid mechanics, compressible flows 101, know that if you drop the pressure sufficiently at the end of that tunnel, you eventually induce a shock. So as this right-hand side value of the potential passes about 1.15, a shock is formed, and the problem becomes nonlinearly interesting. How interesting? Well, here's the left-hand diagram showing in dashed curves the difficulty that a standard global Newton method has with this problem. And this is done for 4 mesh resolutions. And you see that the finer you make the mesh, the harder it gets for Newton to locate that shock. But once the shock is located, it drops the solution into it with a very quick quadratic convergence. And on the right here, you see successive values of the phi of x function through 55 iterations of a standard inexact Newton, whereas the NEPIN preconditioned version always finds the root very quickly, with a little extra work, of course. And if you compare NEPIN, the left version, and INB-NE, the right version, what we've done here is basically taken the mesh points in that region as a potentially bad, there are ways to get it closer in the 2 different methods, but to have a uniform selection of bad to compare the 2 methods, that's the subset that was chosen. And you can see they both converge in 13 steps, but not through identical iterates. And there are some sort of jogs in the solution at the boundaries of the unknowns that are excerpted for special treatment. Let's, so if we look at a better way of picking the bad points, it would be related to monitoring the Mach number as it begins to rise and form the shock. So the details are in the paper, but we can hypothesize a cutoff Mach number and only identify the points around there. And let's look at a 2-dimensional version of this. So we have the transonic potential flow PDE in equation 26 there, where the density as a function of the potential has this nonlinear form. And we can take a section, where this is the top of the airfoil, use injection to parameterize that shape, set up a standard problem. This is one that they do. This is a formulation they used a lot in the 80s and 90s at Boeing before gluing on boundary layers and viscous effects. And it's indeed there, Boeing's form of density upwinding that we use within this 5-point star actually extended to extra pair of points in each of the 2 dimensions, and a standard switching function. And this is a Mach contour plot showing in yellow the supersonic region that forms near the leading edge of the wing, and the pressure coefficient showing the shock. This plot here is the middle third of this here. And this is on a uniform 512 by 512 mesh. And you can see again in red the inexact Newton with backtracking for 3 resolutions, struggling to find the shock and then converging right away, whereas the nonlinear elimination knocks it off early. A comparison of all the iterates, it's just sort of walking 1 mesh point at a time per Newton correction, throwing away all the work of all those global linear solves, walking a mesh point at a time instead of just finding the shock and converging. And these are on Newton steps 2, 4, and 7, the points that it identified as bad points. So, a rather modest subset of the 2-dimensional field. Of course, if the mesh were adaptively resolved, it would be a bigger part of that subset. But, you can get an idea that there's some efficiency in trading global Newton solves for these local ones. So let's go to a more serious problem. So that you have Darcy's law for velocities of a wetted and a non-wetted phase in a reservoir problem. Phi is the porosity now, and K is the permeability. And so the second equation is sort of the continuity equations for the saturations of water and, say, the oil. And this is a standard problem in reservoir modeling. K is a tensor, and it's anisotropic and inhomogeneous in general. It can range over many orders of magnitude, the porosity between 0 and 1, and various other physical effects that we either don't have time to explain well, or you know them all, depending on which side of reservoir modeling you're in. But the initial condition will be, all the pores saturated with oil, and then we'll inject water in the middle and try to drive the oil towards the boundaries. And these are the input, outflow, and fixed boundary conditions. So this is going to be solved by a fully implicit time discretization and a discontinuous Galerkin spatial discretization. Eventually, you come up with a set of nonlinear algebraic equations at every time step, which can be either in terms of the 2 saturations. No, they sum to 1. So you're going to have either pressures or velocities on 1 saturation. And a typical choice is to have a pressure and 1 saturation. And this leads to methods like IMPs, implicit pressure, explicit saturation, which is the standard model in the industry. It's an operator split kind of a solution. It doesn't give you, the stability of a fully implicit temporal approach. I think it's not necessary to defend discontinuous Galerkin as a choice. The standard in the industry is typically finite volume, but discontinuous Galerkin has many benefits. But one that I think is especially important is that when you go to high order, you don't have a big halo. It's very useful for parallel computing with domain-type decomposition. So software is going to be libmesh for the finite elements, PETSI for the algebraic solvers, and Shaheen 2, our supercomputer at KAUST, our Cray XC40. And just to justify the discretization, there's a standard problem called Buckley-Leverett, which is a 1-dimensional water flood of an initial oil-saturated reservoir. It has an exact solution, which you can barely see in black here, and an industry standard method with IMPs and 2-point flux approximation in the control volumes using the MATLAB reservoir simulation toolbox from Syntef, for example, shows a little bit less fidelity to the exact solution than the fully implicit discontinuous Galerkin. And here you can see that mesh resolution for the DG method is quite satisfactory. So in a two-phase problem in 2 dimensions, we have a choice of how we identify the bad degrees of freedom. So one possibility is to look for high residuals, which may occur near the sources and sinks or near particularly transitional places in the permeability tensor, for example. Another possibility, just to mimic the industry standard, is to say, okay, all the pressure unknowns are bad. Let's eliminate them separately, and then the saturation, and then feed those two into the global Newton. So the first one there is that multiplicative field split approach, pressure, saturation. And the second one treats pressure and saturation together with a geometrically isolated subset of points. So let's look at a 2-dimensional problem with this porosity field and this permeability field. And it's log on the right, so there's about 5 orders of magnitude in permeability there, and a couple of obstacles. And we'll inject in that red well in the middle and produce at the 2 wells in the corner. And if the permeability is homogeneous, you get a rather nice behavior. For the 3 heterogeneous cases, you can see that it's disturbed. And the main difference between this one and these 2 is that these 2 have activated the capillary pressure B sub C in this model. So here's some examples of performance over a certain number of time steps. Inexact Newton with backtracking is the upper pair, then INB-NE with the field split, and INB-NE with the coupled element block. I think the most important thing to point out at the beginning is the total time to get to a physical model time in the simulation. It's not dramatically better, but it's certainly better, and it's certainly better once you turn on the capillary pressure, because then Inexact Newton does not converge at all. But in the cases where it does, we can still improve on it with nonlinear preconditioning. And these on the right show the number of Newton steps per nonlinear iteration phase. No, that's a total number of Newton steps per time step. The inner Newton steps for the subproblem elimination, the linear solves per that subproblem elimination, and a significant amount of the total time is actually devoted to the inner problems, which is what we sort of want. We want to have very little work at the outer level. And here's a case with 0 capillary pressure and a case with high capillary pressure. The black curve fails to converge. That's Inexact Newton with backtracking. These are 3 different time steps, time step 1, 5, and 10. And so we get good convergence in the case where INB fails, and better convergence in the case where INB succeeds. And this kind of behavior has been seen in arterial flows and combustion problems, and probably problems that are in your own sphere of interest. Here is the Newton step length. So initially it's damped, and then it dies, whereas in the 2 preconditioning methods, it may accept full Newton steps on the outer from the beginning, or it may be damped, but eventually it goes to a full Newton. And by the way, this curve motivates one of the small topics later in the talk, namely how do you switch off in the preconditioning when you no longer need it. Just a little bit more detail on a little more sort of visualization of what's going on. You can see a subset of the 2D domain near the injector. This is before, this is after. So the before, this is for the pressure saturation split system. Pressure on the left, saturation on the, saturation on the left, pressure residual on the right. And notice that the scales are different. So it's about 2 orders of magnitude smaller in the vertical, showing the residuals. And this is the residual that's being fed to full Newton, and this is what's being fed to full Newton after that preconditioning. And for the coupled element block, similar pictures. So as I say, it's a very simple method, but it has probably broad applications, and it's easy to see why it works. And for the coupled element block, here is the succession of points at the 200th and 400th time step of the physical evolution that are highlighted for elimination. And here is the before and after for the wetting saturation fluid at those same two time steps. And now we go to the 3D test problem from SPE 10 with this porosity ranging from about 1/20th to about half, and that log of permeability. And here's some shots of the evolving saturation. Blue is oil, and the red is pure water. And this is the plot I showed you to motivate the talk at the beginning. And this shows that there's, you know, a decent amount of strong scaling. No method strong scales over too many decades, but you know, there's at least a good amount of scaling here, especially considering that the nonlinear elimination introduces load imbalance, which is, you know, sandwiched between bulk synchronous phases. So a little bit of perspective now on other aspects of nonlinear preconditioning, hopefully leading to, you know, some good questions. The original method goes back, as I said, 20 years to something called ASPIN, Additive Schwarz, Preconditioned Inexact Newton. This was a domain decomposition method, a nonlinear generalization of the additive Schwarz, which was popular at that time for parallel computing of elliptic and parabolic PDEs in particular. And in domain decomposition, of course, we divide a given domain into subregions and solve problems on each of them, and then try to glue together a solution in some bulk synchronous way. Having done the bad good ritual earlier, the generalization, which really is, the order of invention was reversed, but it should be easy to follow what you're doing in the additive Schwarz version. We find a correction on each subdomain. The subdomains may overlap or they may be non-overlapping. And then we do that by eliminating within that subdomain and keeping all the other unknowns, which are on other processors anyway, fixed. So it's a very parallel method. And then you sum up those T sub lambda i's to form the new nonlinear residual, the thing which may have a problematic Jacobian, because after all, there's a lot of implicit solves in there. It's no longer your original PDE discretization. So this is a domain split version. You could also imagine a field split version in a multi-component problem where you find subresiduals G and H from the original problem, and you create them by eliminating first within this original discretization the U unknowns and then the V unknowns. And this is an additive version where those are done separately and therefore potentially in parallel. In the linear case, if you did not have overlap, then ASPIN reduces to standard block Jacobi. So it sort of devolves to the right thing. You have a diagonal block preconditioning matrix inherited from the subdomains, and now we just generalize that to Newton solves in the subpartitions. Of course, this can be made multiplicative, as in a Gauss-Seidel method, where after eliminating in the first set for G, you take that into account in the elimination for the V's. So the notation here for later slides is capital G and capital H are the original formulation. Little g and little h are the residuals, which become the, they're the corrections of the original, which become the residuals of the modified. And the Jacobian of that preconditioned system can be worked out by the chain rule and some other manipulations as follows. And in this multiplicative version of the field split method, there is a triangular solve which can often be approximated by displacing the arguments in drawing Jacobian blocks from the original. So let's apply this to an easy to understand two-dimensional driven cavity in velocity vorticity formulation, where the only nonlinear term is the convective terms for the vorticity in the third equation. And so that Reynolds number will control the degree of nonlinearity and give us a parameter to play with the necessity of preconditioning. So in the top, you see the figure that I showed at the very beginning of inexact Newton with backtracking failing for a Reynolds number of between 100 and 1,000. And that green line shows the 10 iteration mark, which is satisfied in spades by both ASPIN and MISPIN. By the way, ASPIN with field split, the block-Jacobi method, is usually not very satisfactory. But ASPIN with the domain decomposition method often is. If you want to do field splitting, it's much better to go multiplicative. Analysis has been done. You can show that if the original root has a non-singular Jacobian and you're extracting blocks from that Jacobian, that you get superlinear convergence and asymptotically quadratic to the same root. So I mentioned the desirability of turning off the nonlinear preconditioning after it does its work and gets us into the domain of Newton convergence. And that's actually a rather simple trick. This is an estimate of the next residual if the linear model is valid. This is the next residual. And so if that ratio is small enough, it says Newton is probably going to work by itself without assistance. So we can set up this simple algorithm that tests on this tuning parameter epsilon. It can be something like 0.1, 0.2. And let's apply that to this problem that we just looked at. And INB converges for Reynolds number 100, fails for 1,000 and 10,000. MISPIN fully nonlinear preconditioned all the time, succeeds at the high Reynolds number, and the adaptive version succeeds in the same number of steps, but those steps can be cheaper at the end. So for 100, 1,000, 10,000, you see the totals of the number of steps, but in the adaptive cases, there's more Newton and less preconditioning needed after just a fast start. Another idea is to sort of cascade the subset of bad unknowns. You may look, for example, at the highest residual or at some Mach number cutoff, or maybe in chemistry it's some temperature, or something in combustion it's some temperature, and isolate first a small number, and then when you eliminate them, they will propagate a large residual in sort of a ring or a ball, and you can gradually increase the amount of points that are eliminated in order to basically economize on the cost of the original solve. And we illustrate that here with a 3D driven cavity. So this is in blue the single layer INB-NE. So this is the right preconditioned version. And I'm not claiming that the high Reynolds number problems here are responsibly discretized. You may not see all the physics, but it's again a control on the nonlinearity of the problem. And for the higher Reynolds number 3D driven cavity from a cold start, even the INB preconditioned version has trouble, but the multi-layer is much more efficient, well, both efficient and effective. It actually works at the higher Reynolds numbers, and where it does work, it's more efficient than the single layer version. So there's another sort of analogy to cascadic multigrid that sort of helps here. And there are some pictures of the bad subsets colored in red in this pair of pictures, and then the actual residual contours after the subspace correction, the ones that are fed into Newton. And they're on a comparable scale. So another cute idea once you have this mechanism set up, oftentimes when we solve PDEs, we don't really care about the field at all points. We care about some functional, like the integral of a flux over a surface, or the value at a point, or some average. And this would be an example, for instance, where we have convective cooling of some semiconductor chips, and we might be interested in the flux over those gamma boundaries, for example. And that might actually converge more quickly than the global solution. And that's something that's actually, there's machinery to monitor that inherited from this overall method. So I bring you back to the script F, which is composed of the corrections, little g and little h, to the original problems, capital G and capital H. And we'll be able to infer the convergence of the state variables u and v on the basis of the corrections g and h with some Jacobian block manipulations. So if you define the shifted variables p and q, which are u corrected by g and v corrected by h, and then define this particular Jacobian, which the upper right block is the same because this was a multiplicative method, but the bottom three are with the modified residual. Define those blocks, B11 through B22. You can work out that the sensitivities of the modified residuals with respect to the original state variables are as such with respect to those Jacobian blocks. Then by Taylor expanding the corrections G and H again about the previous points, you can get them expressed in terms of the change of u from the previous u point and v from the previous v point. And that triangular system of two linear equations is trivially solved for the corrections to u and v based on the updates G and H. Now suppose we want to know some linear functional of u and v, the original state variables, which can be defined by inner product of some phi1 and phi2 with those. So phi1 could represent a discretization of normal derivatives integrated along a tangential direction to get a flux, for example. So we're interested in this quantity as our output. We have a succession of intermediates, which by the expansion on the previous slide can be related to quantities in G and H, which is what we are monitoring as part of the nonlinear convergence. And here's a little theorem that bounds the difference between the asymptotic L and the current kth step L in terms of the evolving quantities G and H and these Jacobian blocks. And so let's apply that to a four-component problem. Again, velocity, vorticity, and now a temperature, which has another nonlinear term with this Prandtl number. And GR is the Grashof number for a natural convection. And let's just create some sample functionals, sort of a midpoint averaged u velocity, a vertical velocity gradient at the midpoint, and the corresponding vorticity at the midpoint, and an area averaged temperature. And run that problem. So those four functionals are shown in those four plots for an evolution of Newton steps on the x-axis and a log of residual on the y-axis. And the thing to notice is that the absolute errors, which are solid, are always bounded by their corresponding, those estimates from the theorem. So if you care about this value being below some point, you could see where it reaches it based an upper bound on it by just tracking the corresponding dotted quantities which are available as a byproduct of the computation, and presumably stop the convergence earlier. So I will conclude with a couple of claims and future prospects. Nonlinear preconditioners can be effective in improving the convergence of global inexact Newton. They robustify, we have no shortage of globalization methods. We have mesh continuation, temporal, pseudo-time continuation, parameter continuation, different kinds of backtracking and trust regions. There are many, many tricks in the engineer's toolkit for globalizing Newton's method. But this is another trick which often obviates the needs for those fancier ones. And it's the only one really that says, let's not solve so many global linear problems with their high condition number and their poor scalability. Let's attack the nonlinearity where it is if we have a good heuristic for finding it. So it does cost more per iteration, but hopefully it does fewer outer iterations, and mainly, therefore, fewer synchronizations of a Krylov method in a highly parallel computation. Also, if you're running Newton in an expensive parallel computation, you don't want it to blow up in an unpredictable way. So really, the robustification is almost more important than the efficiency in some ways. There's an adaptive framework that allows you switching back to Newton when it is safe to do so. And there are a posteriori error bounds on the linear functionals of interest because you may not need to drive the Newton to a high convergence to get to a certain accuracy of quantity of interest. There are these cascadic ideas to be pursued that may reduce the cost of the preconditioning steps. I put that bullet in because you have to mention the words machine learning in any talk now. I don't have any good ideas, but there will be ways within a class of problems that a user is familiar with of getting better heuristics, I'm sure. There are, of course, load imbalances introduced by different Newton solves happening simultaneously or on subsets of degrees of freedom, where other processors in a domain decomposed approach are going to be idle. So this suggests retreating from our bulk synchronous processing to more task-based runtime systems like Parsec, StarPU, Quark, and the like. And that would be one way of overcoming the inhomogeneity of work of the different Newton subsolves. And yeah, so I guess that's what I'm referring to in both of those bullets. And I'd like to, not because I'm at MIT, but because I love this quote no matter where I am, from Gil Strang's 1986 book on Introduction to Applied Mathematics, a very progressive book at the time. At this very moment, the search is on. Every numerical analyst has a favorite preconditioner, and you have a perfect chance to find a better one. That was true when it came to linear preconditioners, which is what this one was about. I think it's even more true when it comes to nonlinear preconditioners because of the need to understand where the problem unknowns are within the system. So your intuition is needed and your collaboration is invited. And if I may work in a couple of job ads at the end of my talk, at KAUST in the Extreme Computing Research Center, we are encouraged to partner with Saudi entities that have various problems. They may be computational, they may be experimental, or whatever. But we recently landed 2 such tasks, one with Daniel Colombo at Aramco, a very clever optimizer, inverse problem seismologist kind of guy, and my new colleague, Matteo Ravasi, who actually has some industry and good academic experience in Marchenko imaging with tile low rank matrix inversion. The other talk I like these days is talk about data sparsity. We have found that there are very simple low-rank approximations to large dense systems that reduce by orders of magnitude the time of using something like scale-a-pack in large dense systems when they arise. And in this case in particular, there is an iterated MATVEC that you see in the upper right, where those R operators consist of an FFT, a dense multiply, and then another FFT. And those dense multiplies can be sparsified to allow, well, the kinds of advances. This is a log scale in time, and this is the dense problems on 5 different progressive architectures: Intel Ice Lake, AMD Rome, Fujitsu A64FX, which is the core of the machine Fugaku, the world's #1 system right now. It's not a GPU machine, it's an ARM machine. And then the new NEC vector engine called Aurora, and the NVIDIA A100, the latest GPU with them. In every case, there are dramatic savings in runtime to be achieved by, first of all, recognizing the data sparsity in the original convolution operator, and then ordering the points in a geometrically informed way, with, in this case, a Hilbert ordering in a multidimensional case. And so this problem is solved, but we want to extend it to other uses of tile low rank in subsurface imaging. And in a separate project, also just funded with Venkatraman Murali at NEOM. If you haven't heard of NEOM, it's a Belgium-sized piece of land in the northwest corner of Saudi Arabia near Jordan, Israel, and Egypt, which is slated to become a carbon-neutral city of several million. I mean, it's really more of a city-state. And already there's a lot of green hydrogen projects going on there. But as with any renewable, there's intermittent availability, and as with any human society, there's intermittent demand. And the difference between those two can be an impediment to the world conquering our climate difficulties. So NEOM is considered like a living lab for a lot of these new technologies. And in particular, we have a new project with Ibrahim Hotet, the person who understands the circulation of the Red Sea better than anyone else. Omar Knio, who's currently the Dean of Computational Science and Engineering, and George Turkia. By the way, this is my own local Lebanese mafia at Coast. And Murali is the NEOM player. And we have two new postdocs on this to basically put these two halves, supply and demand, together with machine learning from both the weather and social models. And if you're intrigued, you can write to me, david.keys@kaust.edu.sa, or grep those folks online. And we're starting these on the 1st of May, but we expect them to be long-term. And I like to draw problems from real applications because then you're not just playing in a sandbox, and hopefully, as in the same case of nonlinear preconditioning, we'll come up with some interesting heuristics. So I think I've taken about 50 minutes, and would be So thank you.
Okay, so we are open to questions now. So if you have a question here in the room, please let me know and just chime in, and I'll give you the mic. For those people that are on Zoom, just write your question on the chat, and we can maybe open the chat and read the question aloud. So first, I'll go for people here. Any question here?
Jaime.
Yeah, Jaime.
Thank you, David. Very, very interesting talk.
Thank you.
I've heard parts of it from you before, but that's actually quite a very nice review. I mean, my question is perhaps more of a comment. I think you alluded to it in the last, when you made the conclusions. Like, clearly, in the context of parallel computing, I could see the advantage of using something like Schwarz decomposition, because then what you call the bad unknowns are identified based on based on implementation, based on the way you decompose the domain, right? But these are not the unknowns that would produce the most stiffness.
Correct.
Ideally, you like to choose them based on some other base physical criteria and so on. But then I could see the complexity when you try to really choose the unknowns by some other means in the context of parallel computing. And how do you do that? Because you may be doing the inner iteration and all the other processors might be waiting.
Exactly.
Unless you bring in some additional complexity as these task managers or things like that. But am I on the right track?
Yeah, your comment is exactly right. In fact, if you go back to the 2002 paper, there's a sentence like in the last paragraph that says, by the way, parallel computing is going to be a real, challenge for this method because of the non-uniformity of each subdomain on its own Newton problem. And as long as we're within the bulk synchronous world, it's a price to be paid. I mean, one might perhaps say, let me cripple the nonlinear preconditioning to improve the load balance and get overall better efficiency, but pay a couple of extra synchronous. There's a lot of trade-offs there. You're absolutely right that within the context of parallel computing, the additive Schwarz method may be more attractive simply because it doesn't need to make a lot of decisions, and it exploits processors that are going to be owning those degrees of freedom anyway. So why not just do sub-eliminations in each domain, whether they're hard or easy? You'll get the hard ones. Of course, if there's some kind of a feature that's split over two subdomains, you're not going to capture that the way you would with a heuristic. But the additive Schwarz feature is definitely much more the parallel method. This finding a bad subset is much more the sequential method, and maybe there's going to be some way of, I like to think of the future of parallel computing as sort of a pool of tasks with different user assignable priorities and different penalties for moving data, and getting away from bulk synchronous, and then these tasks can be handled maybe in a bulk throughput way more efficiently. But for now, the parallelism is a challenge. I mean, you saw that the strong scaling wasn't perfect in the driven cavity.
Yeah. Just another one, and that's actually of direct interest to us. But I mean, with these GPU machines and the way they work, these matrix-free approaches to solving nonlinear systems have really become increasingly more popular for obvious reasons. Have you seen of any implementations trying to avoid the use of the computation of Jacobians? And how would you go about that?
Yeah, so the Frechet derivative, the Jacobian vector product of the original matrix is of course easy. The Jacobian vector product with the transpose is, it almost says, compute the Jacobian and transpose it. There is actually a way of selectively generating columns of the Jacobian transpose by matrix multiplications with the original Jacobian. I mean, you have a bunch of E vectors, and you hope that will be lower than the full dimension. But I don't really know of a matrix-free way of getting Jacobian transposes after all this time, And so, the use, on the other hand, of GPUs is almost an orthogonal issue. I mean, PETSI now has, if you're using GPUs in your app, you can probably declare that space and have PETSI, do its work on the GPU without moving the data back. Nowadays, that's an increasingly, available functionality. It hasn't permeated the whole tool chain, but GPUs are proving to be much less of a challenge than they originally looked at. Just like MPI, ended up being much less of a challenge than everybody feared. They are asymptotically, energetically more efficient, and we will, probably use them even in their inefficient ranges rather than move data back and forth. Leveling trees and finding uniform batches, which there's a lot of tools in finding subproblems that let you find collections of tasks that are 64 threads or a warp or something. There's a lot of ways of structuring the inside linear algebra operations that are more and more amenable to GPU style SIMT. And the interesting thing is GPUs and the ARM. This A64FX, the world's fastest machine, doesn't use GPUs, and it's on top of top 500, top 500, Graph 500, HPCG, and HPAI, and it's not far from the top on Green 500, and it uses the ARM multi-core processor. So we'll see how that contest plays out. It's a fascinating one, but GPUs turned out not to be as scary as we thought, even for adaptive methods like hierarchically low-rank matrices, if we can impose algorithmic constraints on the block sizes and so forth.
Thank you.
Yeah.
Okay. So we are already over time, but let's take one question from the chat.
Yeah.
So is the method somehow equivalent to a fixed point iteration on the splitting button good systems?
Okay, so the original nonlinear Schwarz method, which goes back to actually Drea and Huckbush of both hierarchically low rank and multigrid. he looked at a non-Newton accelerated version. So you could think nonlinear preconditioning in a Richardson way. So you can just think of solving these subproblems and iterating between them without putting an outer Newton on them. If you have a monotone elliptic problem, that will converge. But it was a method that never really caught on, and it really caught on after you wrapped it. You wrapped a nice Newton method on the outside. So yes, there is a non-accelerated version, just nonlinear additive Schwarz. It's been written, and some things have been proved about it, but I don't think it's in wide use.
Okay, thanks a lot. So yeah. I think that with this we are gonna end the seminar. So thanks a lot again for coming here, especially in person. So it's always very nice to have people.
It's such a delight
to
have hybrid meetings again, and thank you everyone who came in, and for all those who are online. I know how you feel. I like to do things online myself now.
Yeah, let's thank David again. So thanks a lot. Thank you.